atomic orbitals worked fine when we were thinking about individual atoms, but they don't work very well when talking about molecules. And then by the end of the class today, I sort of want to pull the curtain a little bit and show you that even this theory of molecular orbitals doesn't explain everything. It explains 99% of everything, but not quite. And so we'll see that there's also yet another theory for explaining how bonding takes place. So anybody want to ask any questions before we start, or shall I jump right in? Maybe everybody needs their coffee. You guys are so quiet. We used to have a nice chat before class started. Now everyone's freaked out in their little house. Okay. Then I'm just going to get started. So last class, we got up to, we finished chapter 4 and we got up to chapter 5. So now we're just experts at how molecular shapes, how we can take a Lewis structure and turn it into a three-dimensional shape. And then we were introduced to the fact that we need different ways of looking at how electrons are shared if we were to actually understand how these molecular shapes are formed. And so I just want to sort of go back a little bit and just sort of introduce what some of the problems were. So the first problem I suggested was that if we just look at a simple molecule like methane, and that there's a problem. And so what I talked about, I'll sort of just want to go over it again briefly, is that we learned with atomic orbitals how to put things in S and P and D and F and all those fun little boxes that we put electrons in. That when we looked at carbon, so here's just a carbon atom by itself. And when we looked at its valence electrons, it had 4 valence electrons, and we had 2s, 1, 2, 3, 2p. So it had 4 valence electrons, and we used the usual rules to place them in these orbitals. So we put them in the lowest energy first, 1, 2, and then we move up to the next highest energy, 1, 2. And so those are the 4 valence electrons for carbon. But then when we actually looked, if you make a Lewis model of methane, the Lewis model looks like this. We have 1 going back, 1 coming out. That when you make the Lewis model, you get a tetrahedral shape. And all these bond angles are 109.5 degrees. We would look it up. It's got 4 regions of electron density. So we look it up on our table. That's tetrahedral. Doesn't have any lone pairs. The shape is also tetrahedral. Made perfect sense. But when you go back and you look at how the electrons in carbon are organized, it actually doesn't make any sense. Because here, we've got 2 electrons in the 2s orbital, and they're paired. So they don't want to bond. And when you look at the other 2 electrons in carbon, they're in p orbitals. And if we go back and remember what p orbitals look like, they were at 90-degree angles to each other. So those 2 electrons would be at 90 degrees between each other. So basically there's a bunch of problems here. We have 2 electrons that don't want to bond at all, and we have only 2 bonding electrons, and they're at 90-degree angles to each other. That's a problem. That doesn't make any sense in terms of 3-dimensional shape. And so the theory that came along to explain this was that what would happen, instead of you having these atomic orbitals, that when carbon actually bonds with another atom or with 4 other atoms or 3 other atoms, depending on how many other atoms there are, you would actually merge or hybridize these, let me go back, these 4 electrons. Oh, here we go. These 4 electrons would actually merge, and sort of you would get an average of some of the characteristics of the p orbital, some of the characteristics of the s orbital. So these 4 would hybridize, and you would take all 4 of the orbitals. So you'd have 1, 2, 3, 4 orbitals. The number of orbitals would not change, but they would be arranged in a different shape. And so we would get 1, 2, 3, 4 s for the s orbital, and p3 for the 3 p orbitals. And we would put 1 electron in each one. 1, 2, 3, 4. And that those molecular orbitals would be higher in energy than the s, but slightly lower than the p, since they're sort of an average of the 4, with 1 in each orbital being able to then bond with the 4 hydrogens. And then we would go back, look at these orbitals, and say, I now have 4 orbitals with equal energy, so all the bonds will be identical. And since there's 4 regions of electron density, they will take the tetrahedral shape that we think it should. And that makes sense for methane. Oh, okay. And now we're going to find out there's a lot of different ways to mix these orbitals that explain some of the shapes. Does anyone have any questions about this so far? How it's clear that the geometry of the atomic orbitals cannot merge with the actual shape we know for methane, because the actual shape, we know it perfectly for methane. Experimentally, we have looked at the shape of methane, and it looks like that. And those are what the bond angles are. That is methane. There's no doubt about that. But that does not line up with what we predicted it would be if we just looked at the atomic orbitals. So does everyone see that there's an issue here? And so we needed a new theory to address it. Still looking at the chat. Everyone's still drinking coffee and worried about the election. It'll be fine. Here are some of the features of these sort of hybrid molecular orbitals. So the number of hybrid orbitals is going to be the same as the number of the atomic orbitals, just like I showed you before. Carbon that had the 1s orbital and the 3p orbitals, they get mixed together, and so you come out with 4 sp3 orbitals. This number of orbitals is the same. The number of electrons, number of valence electrons is the same. Everything is the same except how they're organized in space, okay? And so the type of hybrid orbitals that you're going to form is going to vary with which s, which p, which d orbitals you're going to use to mix them. So the shapes, the types, and the orientations of them will depend on how many orbitals you're mixing together. If you're mixing 2 together, they're going to be linear. If you're mixing 3 together, they're going to be trigonal planar with 120-degree angles. And as you just saw, if we mix 4 together, they're going to be tetrahedral with 109.5-degree bond angles, and so on and so on and so on. The whole point of doing this is this last point right here. It's really, really important, and it's something that I'm going to come back to again and again, and we're going to talk about it in lab this afternoon. The shape, not just the orientation of these hybrid orbitals, but the shape of them is critical. Because if you remember a little while ago, we talked about how orbitals overlap, and that's how we form bonds. That's the whole basis of covalent bonds. So if we have and we talked about hydrogen first. So hydrogen looks like this, right? It just has the two 1s orbitals. Here's one hydrogen atom. Here's the other hydrogen atom. When they come in close enough in contact with each other, these parts of the orbitals will overlap. And so now we'll have two electrons, 1, 2, in that space, forming a bond. So those two electrons will be held in that region, attracted to the nucleus here and the nucleus here. And so they'll be equally shared, and they'll be, sort of basically moving back and forth in a straight line between the two nuclei. And so those s orbitals overlap. The better the overlap, the stronger the bond is going to be. So if I have two p's that are basically the same shape, remember the s orbitals are larger, they're big like this. The p orbitals are slightly narrower. If I get overlap here between two p orbitals, that's going to be an even stronger bond because there's more overlap, there's less space where all those electrons can be. You want to keep the electron density in as small an area as possible. The smaller the area, the stronger the bond. And so the shape and orientation of these hybrid orbitals helps to maximize overlap. It increases that overlap. It lessens the space, and so it increases the overlap, and you get stronger bonds. So let's have a look at what some of those hybrid orbitals look like. And we started with looking at beryllium. Beryllium only has two basic electrons for bonding, two valence electrons. And so because it only has two valence electrons, it takes one of the 2s electrons and promotes it into p, and then mixes them so that you have two sp orbitals. So here's the sp orbital here. And you can see it looks a little bit like an S and a little bit like a P. And so it basically helps, it's sort of halfway between S and P. And it helps increase the overlap that you would see. You get better overlap with a p orbital than you do with an s because the s is bigger. And so basically by combining the two, you increase the overlap. You form two sp hybrid orbitals. And so because you have two regions of electron density, you have one 2s and one 2p atomic orbital to make two sp orbitals, that results in a linear orientation because you've got two regions of electron density. And we already know from the last chapter that if you have two regions of electron density, the maximum distance you can put between them is in a line. And so that is why beryllium dichloride is linear with 180-degree bond angles here, because that's the maximum distance you can get from those. So here's what the hybridization looks like. Again, here's our 2s orbital that's totally filled. Now, according to atomic orbital theory, that really shouldn't bond at all because it's got two electrons in there. They're paired up. That should be it. But it does. It forms two bonds. So we mix a 2p and that 2s orbital together. We only need two orbitals. Why? Well, there's only two electrons, that's why. And so we put them together and they make two bonds, one in that direction, one in that direction, 180 degrees apart, okay? So we got our 2s here. Oops, let me go back. We have our 2s here, and it mixes with one of the 2p's. So this just shows you the shape again. So I want to take you back to what the shape looks like. Now remember, these are 90-degree angles between the p orbitals. But when I mix the s and the p together, I get this shape here. And it's this part of the orbital that forms one bond, and it's that part of the orbital that forms the other bond, okay? And the shape of them looks like this. So I've got my chlorine coming in, and if you remember, chlorine has how many valence electrons? Chlorine valence electrons, how many?
7.
7. It has 7 of them. And so there, the 7 electrons are in S and P, but the single electron for bonding is in a p orbital, if you remember. So chlorine would look like this. Chlorine would have 1, 2, and then it has the p orbitals, 1, 2, 3, 1, 2, 3, 4, 5, for a total of 7. So it's this electron right here that's actually for bonding. And so there it is. The 3p electron from chlorine, that's the single electron, overlaps with the sp hybrid orbital of beryllium, one on one side, one on the other side, and you get a linear molecule. So any questions about I'm having a hard time talking this morning. Orbital overlap is basically the key, is the name of the game here. The more orbital overlap you can get, the stronger the bond is. So our hybridization does 2 things for us. Well, it does more than 2, but 2 main things it does for us. It provides the shape that we're looking for, and it provides better opportunity to overlap with the bonding electrons coming in from another atom. The more overlap, the stronger the bond. Then when we get to 3, remember when we get to 3 electrons required, like you have in boron. Boron is one of those elements that violates the octet rule because it's only got 3 electrons. So it can only form 3 bonds rather than 4, whatever else. It can only form 3. And so it has 2 in its 2s and 1 in the 2p, but it forms 3 bonds. So what it does is it hybridizes 2 of the p orbitals with 1 of the s, mix them together, and now you get sp2. And like I said before, when you have 3 regions of electron density, the most stable way to put those 3 together is in a plane with 120 degrees separating them. And that's what you get with boron. You get these planar molecules, trigonal planar molecules, like this. So again, it's bonding with halogen. This time it's fluorine. So fluorine's lone electron for sharing is in the 2p orbital. Chlorine is 1 bigger, so its bonding electron is in the 3p orbital, and then bromine would be in 4p, and so on and so on and so on. But this time, fluorine's in the 2p. It overlaps with the sp2 hybridized orbital of boron, and this is the overlap right there that forms the covalent bond. And you see we get our 120 degree bond angles, okay? And then methane, we talked about methane. This was the original problem introduced. And so now, since we have 4 regions of electron space, we need 4 orbitals. Well, luckily, Carbon has 4 orbitals that it can put electrons in. It has a 2s, and it's got 3p orbitals. That's why it can make 4 bonds when it hybridizes these. And then, since you have 4 regions of electron space, you get our good old friend tetrahedral with 109-degree angles. And you can see the overlap between hydrogen's 1s, its single electron, and the sp3 hybridized. They overlap quite nicely. And so you get strong bonds there. But we sort of run into the problem. What about electrons? What about if you have more than 4 electrons for bonding? What if you have 5 or 6? What if you have lone pairs? Then that doesn't really, is that going to help us explain what's going on in those situations? So if you look at nitrogen, nitrogen has one more. Now it has 5 valence electrons. It's going to form 3 bonds. And so immediately one might think, well, if it's going to form 3 bonds, then it's going to be sp2, and it's going to look like boron. But the problem with that is we forget about the lone pair. We forget about the lone pair, which is here. That is a region. Remember, when we were looking at the different shapes of molecules, we had to consider the lone pair. We can't see the lone pair, but it influences the shape of the molecule. Because if we don't, with 3 bonds, if we don't consider the lone pair, we would assume that ammonia is planar, but it isn't. We clearly know that it isn't. We know what the shape of ammonia and the bond angles and everything else. We know that exactly, and it's not planar. It is tetrahedral group. It's in the tetrahedral group because it has 4 regions of electron density. We have to remember the lone pair. So since it has 4 regions of electron density, it does the same hybridization that carbon did. It takes the 1s orbital and the 3p orbitals and hybridizes them just like carbon to form sp3 orbitals. But when we put the 5 electrons in it, we notice we put the electrons in there just like we would in a normal orbital, 1, 2, 3, 4, and then go back and add the 5th. And when we add the 5th, we get a lone pair. So that in one of the hybridized orbitals, we have a lone pair, and there it is, right there. So you get the tetrahedral group, you get the tetrahedral geometry, but you get the trigonal pyramidal shape. And that's the shape we actually see. So remember, you have to take into consideration the lone pairs. They will have the geometry of the 4 electron density grouping, but the molecule itself won't have a tetrahedral shape. The molecule will have a shape inside that group. And when you have 1 lone pair, you get this trigonal setup. And then we looked at water. Same consideration. The oxygen is the central atom this time. It has 6 valence electrons, but it only has 4 regions of electron density. So if it's got 4 regions of electron density, sp3. That's all one of the things you really need to remember. It's not as hard as you think if you just go back and look, ask yourself, how many regions of electron density are there going to be, including the lone pairs? And then you just add up orbitals. If there's 4, then I take my s and my 1, 2, 3 p's. Oh, that's 4. If it's 5, we add a d. If it's 6, we add another one. And then you just add them together. In this instance, because we need 4, we go 1, 2, 3, 4. Oh yeah, that's sp3. We make our 4 sp3 orbitals with our 6 valence electrons for oxygen. And we go 1, 2, 3, 4, and we come back 5, 6. Those are our 2 lone pairs. And remember, oxygen almost always has 2 bonds and 2 lone pairs. And this is why. Because it has the 6 valence electrons. Generally, 2 of them are going to be doing the bonding, and 4 of them are going to be in lone pairs. That's just basically that's how oxygen rolls. And so when it's regardless of the hybridization, actually. So in this instance, when there's 4 regions, it's sp3 hybridized. Here's our 2 lone pairs. And then we get, since it's sp3, that means 4 groups, that means tetrahedral. But what's the actual shape? We need to look at the lone pairs. The actual shape tells you that it's bent because of the presence of the lone pairs. It's a bent shape, but a tetrahedral orientation. And then when we get to 5 groups, oh, I want to point out, I have posted this table in Canvas under chapter 5. So if you want to, there's a table coming up that basically has all this information together. You can print it out or whatever you need to do. Because yeah, again, I don't want you to memorize this stuff. I just sort of want you to understand where it's coming from. So here we've got phosphorus. Now phosphorus is in the same group as nitrogen. It has 5 valence electrons. But phosphorus can do something that nitrogen can't. Phosphorus can make 5 bonds. Nitrogen has 5 valence electrons. How come nitrogen can't make 5 bonds? Phosphorus can do this thing here. Nitrogen can't do this thing here. Nitrogen cannot make more than 4 bonds, even though it has 5 valence electrons. Phosphorus has the same number of valence electrons, but it can make 5 bonds. Why? No one wants to talk. Yes, right. It's because it is the d orbital. Remember when we said that elements in the 3rd period can violate the octet rule. We all just sort of said, yeah, it can violate the octet rule. Whatever. Yeah, violates the octet rule. I don't know why, but yeah, sure, that makes sense. This is why. And when we say it can put electrons in d orbitals, what we actually mean is it can take d orbitals and hybridize them with the others. So with 5 bonds, we need 5 regions of electron density. Well, nitrogen ends at S, 2s, 2p, that's it. It doesn't have any more orbitals, doesn't have any place to put any more electrons. Phosphorus has the 3rd, it's up in the 3rd shell, where there are S and P and D. So it has access to these different orbitals. So now that it needs 5 areas to put staff electrons, so 1, 2, 3, 4, 5, and then mixes them together. And so since we have 1 S, we go, it is S, it has 3 Ps, so we go 3P, and oh, it's got a D. So we call that sp3D. In England, for some reason, they put the D first. I don't know why, but over here, we put the D last. Whatever. sp3D. And so now we have 5 places to put valence electrons that are all equal energy. That's another thing I'm going to come back to again and again. I want to show you why this is such a good model for binding. Each one of these bonds is exactly the same. It has exactly the same strength. at exactly the same bond angle. Everything about it is identical. And that's really only possible if you have 5 bonding electrons that are identical to each other. They have to have identical energy, or this structure won't hold up. And so it's the hybridization that gives you 5 identical bonding electrons that's essential for making these sorts of structures. So now that you've pulled a d orbital in and mixed them all together, now we have 5 regions of electron density. And now we have good old trigonal bipyramidal shape, where we have sp3d orbitals overlapping with the p orbitals of incoming chlorine. What about if you have 6? Oh my God, what if you got 6 there? Like sulfur. So this is the same situation between nitrogen, as nitrogen is, remember the old SAT questions? They don't ask these anymore. As nitrogen is to phosphorus, oxygen is to sulfur. It's one further down. So oxygen also has 6 valence electrons, but again, it can only form at the max 4 bonds. Sulfur could form 6. And the reason it can form 6, it can generate 6 regions of electron density equal to each other because it's in the 3rd shell. It has electrons in 3s, 3p, and it can now recruit 2 d orbitals as well. Hybridize all of them together. So now I have 6 regions of electron density. I have 6 different orbitals that are all exactly the same. And since I have 1s, 3p, and 2d, I call this sp3d2 hybridization. And so now I have overlap with these bizarre looking orbitals and incoming atoms, in this case fluorine. And since I have 6 regions of electron density, that's an octahedral shape. Okay, and then again, just like the other shapes, if I have 6 regions of electron density, doesn't necessarily mean that the molecule is going to be octahedral. That depends on the number of lone pairs, but the overall geometry is going to be octahedral. Okay. So this is what I put in chapter 5. This is what you can basically refer to when you have these questions. So basically, all you need to remember at this point is how many regions of electron density is that molecule going to have? Now, it's something I saw on the can there be sp2d5? No, because basically you need to have you need to take all the lower energy orbitals first. And so you have to use all the P's before you start using the D, okay? So yeah, can't do that. Yes, let me get back to, sorry. So what you need to remember is the number, when you draw your Lewis diagram, and basically all of these are going to start with Lewis diagrams. Like for instance, I'll ask you, okay, here is phosphate. Draw the Lewis diagram for phosphate and then give me what the shape is going to be along with the hybridization of phosphorus. So then you go back and you draw your Lewis diagram. You count the number of regions of electron density around phosphorus. And how many would that be? How many regions of electron density would there be around the phosphorus? PO4, how many phosphorus in the middle? How many regions of electron density around the phosphorus? Right, Ariane, 4. It doesn't matter how you draw it. That's the cool thing. If you can draw it, let me just quickly. You can draw it in a couple of different ways, and it makes no difference. Like, for instance, you can draw it like this, with all single bonds on the oxygens, and 1, 2, 3, 4 negative charges on the oxygens and 1 positive charge on the phosphorus, and all single bonds. That's 4 regions. That's going to be tetrahedral. Well, what if I take one of the lone pairs of this oxygen, move it in here to make a double bond and reduce my formal charges? Now I've got this. Negative, negative, negative. No charge on the oxygen, no charge on the phosphorus. Well, guess what? You still have 1, 2, 3, 4 regions of electron density. That's still going to be tetrahedral. Now the shape may be slightly different, because here you've got a double bond, and on the left you've got a single. That will affect the shape somewhat. You may change some of the bond angles, but the overall shape is still going to be tetrahedral. And the hybridization of the phosphorus will be the same, interestingly. So we'll talk about that when we talk about double bonds. We're definitely going to get to that. Okay, so what you need to remember about this is how many regions of electron density are you going to have? So that's what you need to remember. So if you have 2, that's what it's going to look like. That's what the hybrid orbitals are going to form. And basically it says how many unhybridized orbitals are going to be left in the central atom. There's going to be 2 p orbitals left over. When you have planar molecule, that's 3 regions, and it's going to look like that with the triangle. You mix 1 s and 2 p together. What's that? sp2. And importantly, as we'll see, you have 1 p orbital left over. When you mix 4 together, sp3. When you mix 5 together, sp3, 5d. So on and so on. So just remember, 2 regions, 3 regions, 4 regions, 5 regions, 6 regions. Now a region, just like we talked about with molecular shapes, a region of electron density, it's the same here, same rules apply. It's a lone pair, it's a double bond, it's a triple bond, or a single bond. There's 4 different things it can be. All of them are just regions. Everything is just a region of electron density. That's all it is. Remember, we're going to look at the differences in electron density between single bonds and double bonds. It's really interesting. But that's all a bond is. It's just a region where electrons are. A lone pair, just a region where electrons are. That's all they are. But a bond is a region between atoms that is being shared. A lone pair is a region of electrons that is not. But they're all involved in determining what the shape of a molecule is going to be. So here's how we go from, just like I said a minute ago, we're going to get a formula. I'm going to say, I want PO4, I want phosphate ion. You draw your Lewis structure. Then you determine how many regions of electron density are around the central atom. Okay, it's going to be 4. That's going to be an overall tetrahedral group. And then you figure out, because of that shape and how many regions of electron density are around the central atom, what kind of hybridization is necessary to make that? So if it's linear, that's sp2. If it's triangular planar, oh, sorry, that's sp. That's sp2. If it's tetrahedral, that's sp3, and so on and so on and so on, okay? Now, let's have a look. So let's see what we can do with a couple of these different molecules. First, we've got methanol. So methanol is going to look like this. So, oops, that's not what I wanted. So I've got a carbon, and it's going to be connected to 3 hydrogens and an oxygen. So that's what methanol is going to look like. So our question is going to be, what should the hybridization be on the carbon? What should the hybridization be on the oxygen? So let's have a look and see how we're going to do this. So you, hey, dogs. So we draw our Lewis structure. We determine the electron group arrangement around each central atom. In this instance, we've got a carbon, we've got a hydrogen. Figure out what the shape is going to be, and then based on the shape, we figure out what kind of hybrid orbitals are going to be required. All right, so let's look at, so I've already sort of given away methanol. So I got 3 hydrogens. I've got my oxygen and a hydrogen. So I've mentioned before, when you have an alcohol, all an alcohol is basically something that has this group on it. OH. Hey! Desperately need to walk or something. Hey! Jerome! Come here. Come on. Come on. There you go. So, this is Jerome. He's the one making all the trouble. Yeah, you are. All right, so let's look at carbon. And let's look at oxygen, and let's figure out what shapes they're going to be. So how many regions of electron density are around the carbon?
4.
4. Yeah, so carbon is going to have 4 regions of electron density. So what hybridization, what will be the hybridization of the orbitals around carbon? Remember, you need 4 regions of electron density.
Tetrahedral, sp3.
Excellent. Yeah. Again, you gave me the shape, and since it's got 4 regions, that's S, P, and 3 for your 4 different places where you have to put electrons. And that means tetrahedral. Excellent. What about oxygen? Let's look at oxygen. How many regions of electron density are going to be around that oxygen? This oxygen right there. Basically, in how many places around that oxygen are we going to find electrons? That's what a region of electron density is.
4.
Yeah, exactly. 4 again. And because it's 4 again, what's the hybridization on that one?
Tetrahedral.
Tetrahedral, right? So the shape is going to be well, is the shape going to be tetrahedral? That's the overall geometry. You're absolutely right. It's tetrahedral. Will the shape be that? Remember, the shape isn't always the same as the geometry.
Bent.
It'll be bent, exactly. Very good. Yeah, it'll be bent because we've got those 2 lone pairs. So because it's in the tetrahedral geometry group, and it has 4 regions of electron density, doesn't it, Jerome? Yeah, it does. What's the hybridization of bonding electrons on the oxygen? We've got 4 groups.
sp3.
Exactly. Yeah, just same as the carbon. So the shape around the carbon and the shape around the oxygen are basically going to be the same. They're both going to be in the tetrahedral orientation, although around the carbon it's going to look like a tetrahedron, and around the oxygen it's going to look bent. So we're going to get down. All right, there you go. So let's have a look and see what that looks like. Yeah, so you get both around the carbon and the oxygen. You get this sort of tetrahedral group. But like was pointed out by one of you geniuses, it's going to, around the oxygen, it's going to look bent, and it does. It looks bent around the oxygen. Now, what in the hybrid orbitals are going to be the same, since they're both sp3. The only difference is going to be that carbon has 4 electrons, 4 valence electrons, and oxygen's got 6. And so when we fill in our 4, we're going to go 1, 2, 3, 4, and all of them are going to be bonding, right? They're all single electrons, so they're all going to be bonding electrons. But with oxygen, we have 4 places to put electrons, but we have 6 electrons to put them in. So we go 1, 2, 3, 4, and then we go 5, 6. This one and this one are going to be lone pairs. This is a bonding electron, and that is a bonding electron. And this is why pretty much all the time you're going to see oxygen making 2 bonds, 1, 2, and have 2 lone pairs, 1, 2. That's basically why that happens. All right, so let's do, so the other one.
I have a question.
Oh, yes.
Why is there no unhybridized for carbon?
Because all of its electrons are hybridized.
Even the empty orbital box on the left side before it was hybridized? Or there's no arrow in one of the 2p's on the left side.
Right, because, this is, the difference is, this is what the carbon looks like in the molecule, and this is what the carbon looks like all by itself. So the carbon by itself is just an atom, has its electrons arranged like this. When it's just in the atom, it has its arrangement, that's the arrangement of its molecules. But, arrangement of its electrons. But when it's in a molecule, it changes those arrangements to look like this. So that's the difference. So the arrow basically takes you from pre-hybridized to post-hybridized. Pre is when it's just the atomic orbitals by themselves, and then after hybridization, it changes. And so, yeah, there's nothing in here. There's nothing in that p orbital, but we need it to put an electron in after we hybridize.
Okay, got it.
Yeah. No, it's a good point, because this is one of the confusing things is, I've got 4 electrons, but I only got 3 orbitals with electrons in them. How come I just don't hybridize the 3? Because that will not give you the shape you need. If you have just 3 orbitals with 4 electrons in them, basically that is going to give you, so we would have sp2 orbitals, and we would go 1, 2, 3, 4. So this would be a lone pair, and then these 2 would be bonds with 120 degrees apart, and that doesn't make any sense. That does not look like methane at all. But if you use all 4 places, all 4 regions, all 4 orbitals to put electrons in, then you get the shape you need. So the other SF4, let's quickly do that. I stupidly need to, here we go to the whiteboard. So SF4, let me make a big one, SF4. So we're going to put sulfur in the middle and have 1, 2, 3, 4. So how many total electrons am I going to have in this particular molecule? Sulfur's got how many? I hear clicking. Man, you should have your periodic table in front of you at all times. What group is sulfur in?
6.
Mm-hmm. So sulfur, I got 6. And fluorine, come on, we got to know fluorine by now. It's got an ene on the end of it, so we know how many electrons that is. What group is fluorine in? It's a halogen. Which group is that? Seven. So we have 4 times 7. So that's 28 plus 6. That is 34 electrons. So as usual, go around the outside, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But I've already screwed it up. So that's 6 times 4, that's 24. We have, that leaves me with 10. We've got 8 electrons in bonds. That leaves me with 2. Where do I put the 2 electrons left over?
In the middle.
Always put them in the middle. 1, 2. So let's figure out if everybody has an octet. So I know the fluorines have an octet because I gave them an octet when I went around the outside. So each fluorine has 2 bonds, has 2 electrons in bonds, and 6 electrons in lone pairs. So they all have 8. They're fine. And sulfur's got how many total electrons? Not valence electrons. How many total electrons does sulfur have?
10.
It's got 10, right? So it's got 2 in each bond. That's 8, and it's got 2 to itself in lone pairs, so it has 10. So it's violating the octet rule. And we'll find whenever you violate the octet rule, you're bringing in d orbitals. So what will be the hybridization of the sulfur? How do we determine the hybridization? How are we going to figure that out? I've been yakking all morning. How do you figure out the hybridization of the sulfur? Because remember, it's going to be the sulfur that's going to be the one that's hybridized, not the fluorines. It's the central atom that's hybridized, because it's the central atom that's responsible for the shape, not the elements on the outside, the one in the middle. So how do we figure out what the hybridization of sulfur is going to be? What do we need to count?
Number of electron regions.
Exactly. Excelente. Was that you, Ahmad? No, that was Erlan. Was it? I can't see any of you. Erlan, was that you? Or Aaron? I can't. Somebody said 5, and you were
Yes, it was
excellent. Was you, Aaron?
Yeah.
All right. Yeah, so we have 5 regions. Excellent. So we have 4 bonds, and we have 1 pair. That's 5 regions of electron density. So if you have 5 regions of electron density, what hybridization is that?
sp3d.
There you go. Excellent. Yeah, so we need 5. So we need one of the S's, well, the only S. We need all 3 P's, and we need a D. So remember, each one of those is a region of electron density. 1 plus 3 plus 1 equals 5. So that's going to be the hybridization around the sulfur. So let me go back to the slides. So that's what sulfur tetrafluoride is going to look like. Just like we drew, it has the 4 fluorines around it and a lone pair. So the central atom is going to be sp3 hybridized. So how are we going to do that hybridization? Let me, where is my annotation? Here we go. So if we draw this is what the atomic structure for the electrons of sulfur would be. So we've got 3s, and then, so just like oxygen, it's got 2 in the S, this time in 3, and then 3p. So 2, it's got 6 total, right? So we go 1, 2, 3, 4. So that's what sulfur is going to look like when it's unhybridized. Since it's sp3 dehybridized, how are we going to make that? Basically, how many orbitals is that? And then I've got my 3D without anything in them. 1, 2, 3, 4. So how do I convert this to this? How many orbitals am I forming? You basically already answered the question. There was 5 regions of electron density, and so we have sp3d hybridization. Therefore, how many orbitals have we formed? How many new hybrid orbitals have we formed? Someone want to say it out loud?
5.
We've made 5, right? So we take 1, 2, 3, 4, 5. So remember, even if there's nothing in the unhybridized orbital, we can pull that in because we need it to place electrons. And so we're going to make 5 new orbitals called sp3d. And how many valence electrons do I have to put in them? This is sulfur. How many valence electrons do I have in sulfur to put in these new hybridized orbitals?
6.
6, right. Just count them up over here. I've got 2, 4, 5, 6. I got 6 electrons. It's in group 6. I got 6 electrons. And I have 5 orbitals to put them in. So let me put them in. 1, 2, 3, 4, 5, 6. So when we look at this, these are my bonding electrons. These are my valence electrons. How many bonds am I going to form out of this? And how many lone pairs am I going to have? These are all the bonding electrons I have. How many bonds are going to form out of this? How many lone pairs will I have?
4 bonds, 1 lone pair.
Excellent, exactly. This is my lone pair, and I have 4 electrons all by their lonesome without a partner. And so when fluorine comes in, one of its p electrons is going to go there, 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 and make 4 bonds with my lone pair left over. So 1, 2, 3, 4 bonds and a lone pair left over. Excellent. Let's see if we're right. Gosh, I hope so. Right, so that's what it's going to look like. We have the right number of bonds, and we have the right number of lone pairs. And so what we're going to see, going forward, is that basically that's how we're going to fill up these hybridized orbitals. We're going to fill them with the number of electrons we need to make single bonds, and that's where we're sort of coming to next. Hybridized orbitals are for making single bonds. That will become apparent. What's another name for single bonds? Anyone remember?
Was it sigma?
Mm-hmm, exactly. Single bonds are sigma bonds. And so hybridized, we're going to fill in our hybridized orbitals to give us the proper number of sigma bonds, 1, 2, 3, 4, and lone pairs go in hybridized orbitals as well. So our lone pair gets into a hybridized orbital. Now, what is the second kind of bond? Anyone know what the second kind of bond is?
A pi bond?
Pi bonds, exactly. Can you tell me what a pi bond is?
Is that a double bond?
Not exactly. It's the second bond of a double bond. So that part, you're right. So we'll find out that when you make a double bond, so if I have carbon double bonded with carbon, one of those bonds is a sigma bond made with hybridized electrons. The second bond to make the double bond is a pi bond, and that's made with unhybridized. Ooh. So we'll see how that's done.
Professor?
Yes.
I have a question on the last slide.
Well,
It's okay. Do you mind going over really quick why we don't put an electron in 3D? On the last slide.
Because we don't have any bonding. We don't need any electrons there, basically. Remember, one of the rules we learn when we're dealing with atomic orbitals, that electrons always fill up the lower energy orbitals first, right? And they fill up all the lower energy orbitals before they go to the next level. The same thing is true with hybridized, with the exception that we'll see soon of when you need to make pi bonds. So here I've got 3s and 3p and 3d, and I've hybridized them. And so basically this goes away, these goes away, and one of the d orbitals goes away. So now I've got 5 new orbitals, and I basically fill those up before I move up to d. So I would have to fill up all of them before I moved up to the d orbital.
Okay.
Yeah. We'll see that rule gets a little tricky when we're dealing with pi bonds, for the reason pi bonds are made with p orbital electrons. Pop your p's. So these are the two different types. As you pointed out, sigma bonds are single bonds. And as I've been showing, or as I've been attempting to show, all sigma bonds are made by end-to-end overlap of those orbitals, like the hybridized orbital and the unhybridized orbital of the incoming atom. So if this is like a sp2 electron and this is a p electron, they overlap each other directly, and I get direct sharing of electrons in between this nucleus and this nucleus. So the electron density for sigma bonds is directly between the two atoms. So here's, if I have my, go back to carbon, carbon. If I have a single bond between carbon, carbon, that is a sigma bond. All single bonds are sigma bonds. That is a sigma bond. And all sigma bonds have electron density directly in between the two atoms. They're not out in space somewhere. They're not flying all over the place. It's directly in between the two atoms. And that makes them stronger because that electron density is right there. It's not going anywhere. And so it's much harder to pull apart a single bond because that electron density is in one place. As we'll see with pi bonds, they're formed with p orbitals. And you remember what p orbitals look like, hopefully, because I've drawn them like 1,000 times. P orbitals have those 90-degree angles in and out. And the p orbital goes both above the nucleus and below the nucleus. So my nucleus is right here in the middle. And so I've got electron density up here, and I've got electron density down there, far away from each other. And that's where the pi bonds are made, by overlapping p orbitals. And that is sideways overlap. Whereas a sigma bond, I'll have direct overlap between them. So like, here's my one orbital from one atom, here's my orbital from another atom, and they directly overlap with each other. But with p orbitals, here's my p orbital from one atom, and here's my p orbital for the other. They don't really come in direct contact with each other. They overlap sideways. And so I have electron density. So if here's my two carbon atoms, one here and one here. There's my sigma bond. And then p orbitals, both above and below, above and below, they overlap sideways. They don't come in like direct contact. They sort of sideways contact. And so now I have some density above and I have some density below. So my electron distribution is all over the place. It's above the sigma bond and it's below the sigma bond as well. And so the overlap is much less than a sigma bond. And so it's weaker. A pi bond is weaker than a sigma bond. And we can actually measure bond strengths of different bonds. And so a double bond is not twice as strong as a single, it's less. And a triple bond is not 3 times the strength of a single bond, it's even less than that. And this is why, because a pi bond does not have direct sharing of electrons in one space. It's diffuse, it's all over the place. I'll give you an idea of what that looks like.
Professor?
Yep.
So a triple bond will be another pi bond?
Exactly. And the cool thing is we'll see how that works this afternoon. You're actually going to do that and draw it, see what it looks like.
So no matter what, every molecule only has one sigma bond? Okay.
Any two atoms could only have one sigma bond.
Okay.
Can't have more than one. Because, remember, look, so here we have good old ethane. So we're going to, actually, this is one of the molecules we're going to look at this afternoon. So ethane is what we would call a saturated hydrocarbon. A saturated hydrocarbon means it has as many hydrogens as it can possibly hold. So there's no double bonds in it, basically, what that means. Just like polyunsaturated oils in butter. If you have saturated fats, that means there's no double bonds in it. It means they don't really move that much and you get butter. But when you start having more and more double bonds, that makes them a different shape and they get more liquid at room temperature and you get oils. So this would be considered a saturated hydrocarbon. So there's no double bonds. So we have just a direct overlap of orbitals. Here's our two sp3 orbitals coming together, because each carbon has 1, 2, 3, 4. They're each bonded to 4 atoms. So they have 4 regions of electron density. So they're sp3. And so there's direct, this is a sigma bond, because all single bonds are sigma bonds. And so you have direct overlap of those orbitals. And so you also have, that's where the electron density is going to be, right in between those atoms. Not out here, not out here, right in between. And so that's basically why you can't have another sigma bond. There's no place for it. We already have electron density between the two atoms. You can't double it up. They would repel each other. So if we have another bond, it's got to be somewhere else. And it'll show you where it goes. So you can see with ethane, now we're looking at the electron distribution. You see it's pretty even all the way around. So would this be a polar molecule or a non-polar molecule? Since there's even distribution of electron density. Polar or non-polar?
Non-polar.
Non-polar, really non-polar. Yeah, it's a very non-polar molecule. So this is a gas, even at like really low temperatures, because it's such a non-polar molecule. But let's look at ethylene or ethene. Ene is when you have a double bond. So you add the word ene. So if we have ethane, means there's no double bonds. Ethene, ethyl meaning 2, methyl meaning 1. Ethene means we have 2 carbons and there's a double bond in there. And so now there are 3 regions of electron density. 1, 2, 3. Each carbon is bonded to 3 atoms this time, not 4. And so now we have sp2 hybridization, because there's 3 regions of electron density. So here's our sp2 hybrid orbitals making a sigma bond, because they directly overlap with each other. So the 2 carbons have sp2 here and sp2 here, and they directly overlap to make a nice strong sigma bond. The hydrogens also make sigma bonds with their 1s orbital overlapping the sp2. But where does the pi bond come from? Well, remember there's 4 orbitals. There's the s and there's the 3 p's. We've taken the s and 2 of the p's to make sp2. So we have 1, 2, 3. Here's our 2s. And here's our 1, 2, 3, 4. And those are our 2 p's. Now what we've done, we've taken 2 of the s's, 1 of the s and 2 of the p's and made sp3. We have a p orbital left over. And so what happens is one of these electrons gets promoted to that p orbital, or we just take that p electron. We have a p electron left over, basically. We have a p electron left over. And so here's our 2p electron left over on both of the carbons. Both of them will have a 2p electron left over. Those 2p electrons are both above and below the sigma bond, because remember, this is what the p orbitals look like. And you can see this is what the p orbitals look like right here. They overlap slightly. And so basically you get this really weird looking bond with electron density above and electron density below. And so you can see that there's much less density in a pi bond than there is in a sigma. The sigma bond has tremendous electron density right between the two atoms. But the electron density of a p orbital is diffuse. It's both above and below. So who's asking me about the triple bond? Because I'm just going to get to that.
Yeah, I was just wondering, just seeing if there was a like sandwich between two pi bond. I mean, yeah, two pi bonds. And
I will show you right now, Captain Segway. So any questions about what the pi bond looks like? It's weird. It's a weird looking bond. It looks like a hot dog bun. So you've got your hot dog is the molecule, and the bun is basically the diffuse electrons both above and below the sigma bond. So just remember, that's why the pi bond up here, oops, let me go back. The pi bond both above and below. So we'd have our pi bond up here, our pi bond down there. So we have much more density in the middle than we do here. So it's a less strong bond. Now, what if we have two pi bonds? What if we have a triple bond? Where are those electrons going to be? Seems like we don't have any room for them. Well, here's acetylene or ethine. Ethine. Oh man, I can't spell this morning. Ethine. There we go. Ine means two double bonds, so it means a triple. Ine means a triple bond somewhere. And so since we've only got two carbons, eth means two carbons. It means there's a triple bond in between them. So now we have two regions of electron density in between. Here's one of our carbons, here's the other one. They're each bonded to two atoms, the other carbon and a hydrogen. So there's only two regions of electron density. Well, if we have two regions of electron density, that is sp hybridization, as we've learned. That also means that this molecule is going to be linear because sp, two regions of electron density, furthest you can get those apart is linear molecule, 180 degrees. This is what that weird molecule is going to look like. So we have direct overlap of the sp orbital in one carbon and the sp orbital in the other carbon. So let's look up at the top here, and that's what that's going to look like. So I have an sp hybridized carbon here, I have an sp hybridized carbon here, and those two sp orbitals directly overlap and form your sigma bond. Always, 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 the sigma bond is made with hybridized electrons. That's really important to remember. It's always hybridized electrons that make sigma bonds. And the reason for that is that's how you get direct overlap. That's the whole point of making hybridized orbitals in the first place, is so you can get good overlap and strong bonds directly in between the two atoms. And that's what you get. You get a strong overlap of the two sp. Now, because we've taken an s and a p orbital, that means there's two p orbitals left over, each with a single electron in them. Here is one of them. Here's one of them. So I have two p's going up and down. That's my 2p on the top there. And I've got two p's going in and out. And that's this one. That's this one. And they're at what? 90-degree angles to each other, just like the p orbitals are supposed to be. Remember, there's px, py, and pz. Remember that? Px, py, and pz. And they were 90 degrees apart from each other. That's still true because these are non-hybridized p orbitals. These are atomic p orbitals. They have not been hybridized. And so they look like atomic orbitals because they still are. And since they're at those 90-degree angles, like they should be, you have two of them going above and below. That's this one. 2p going above and below. And the other one is coming in and out. And they're going to be at 90-degree angles from each other. So I make a pi bond on the top and on the bottom, up and down, and I make another pi bond in the front and behind. And so basically, I make a completely covered hot dog this time. So I've got two buns on the top and bottom, and I've got a bun on the two sides. And so that's where my second pi bond goes. Because if I put them anywhere else, they're going to repel. So you put them at 90-degree angles from each other, that gives them the greatest distance apart. Excuse me. That puts them the maximum distance apart from each other. Okay. Now my group this afternoon is going to work on this, make some, pretty pictures and stuff. The rest of you, what I can do is you can go to the websites that my group will be going to this afternoon, and you can see like what the orbitals will look like. You can see what they look like in like real time, and you can make them yourself. And there's I also in the instructions for the lab, there's a good website that explains a lot of this. Actually, I can also post that under chapter 5 as well. And someone asked about videos in Canvas under chapter 5. There's a bunch of videos on this as well that I would recommend, just in case. So, any questions before we go? I imagine there will be one or two. These are cool pictures, though, right? Now you see them. See, this is where it really hurts not being in person, because in lab you would actually make these, and you could see, in working with your hands, how they're put together. So, any questions before we go? I swear, all the ballots will be counted by the weekend. It'll all be okay. Yes.
I have a question, but I guess it's something to do if we could do something in your lab.
Sure.
I have the molecule kit, and I was.
Oh, you do? Oh, awesome.
I was wondering,
how did you get a hold of that?
My last chem, I actually dropped it, but I knew we were gonna need these, so I ordered it.
Cool. Yeah, that's so awesome. I'll have to put you on screen this afternoon. You can show what it looks like.
Okay, for sure. But I was just wondering, because I'm not too sure how to go about making like the p orbitals with it and stuff. So if you could kind of direct me into like instructions on how to build the model.
Sure. Yeah. Okay. Well, I don't know exactly which model you have. Some of them have p orbitals, and some of them don't. You might have one that just has the short connectors for sigma bonds and the longer connectors for pi. So
I'm not sure if you could see this, but it has like all those like.
Oh, it does. Oh, sweet. Okay. Yeah, we'll have a look at that this afternoon.
Okay.
Yeah.
Okay.
Awesome.
All right.
I
Thank you.
also had a question.
Yes.
How are we going to show, is there a part where we're going to show our data, or is there not going to be a way to show our data for this lab on the lab report?
You'll be making drawings to show your data.
Okay, got it.
Yeah. Yeah, hopefully you can draw better than I can, because my as you can see, I have trouble, drawing a stick figure with any convincing effort. So, but that's basically what we want to do is we want to we put these things together piece by piece, and then as we add our p orbitals, then we can see where the pi bonds are. But yeah, that's what the websites will help us do. We sort of build them piece by piece so you can see how they fit together. Because it's these are a little hard to make out. I mean, especially this. It's kind of hard to make out, but it's a good way of sort of seeing before you add the bonds. This is what it looks. This is why it's linear. And then this part, when it shows you the electron density, sort of basically shows you what the shape around the molecule is going to look like. Any other questions? Okay. I'll see some of you this afternoon. I will have, yes, send me any if you have any questions, either post them on Canvas, send me by email. I'll be trying to get caught up on grading, but as you can see, it's kind of difficult. I'm trying to put together all these labs and everything else at the same time. We're all working very hard. Anyway, we'll see you this afternoon. I will talk to you either on the weekend, or I'll see you on Monday at office hours, or next Tuesday. All right? Stay well. Don't get too depressed this weekend. It's all going to be fine. All right. Bye-bye.